Okay, so I'm David Freitag, and this is Makefiles, but in English. So, what's Make? What can it do for us? And what is a Makefile? So, most of you are probably used to, on the left there, just running your GCC lines directly to compile your one file, which is built into your binary. But if your source tree contains multiple source files, or you have multiple directories, it's an actual tree, running each command by hand gets out of hand really quickly. So Make exists for automation. It basically is, it's built on top of Bash, so anything that runs in Bash has a CLI will work for Make. You can do literally anything. But for the purposes of this talk, we're just going to be talking about C. So Make has a few implicit rules built into it, which we'll see in the next slide. And those, it's basically C, C++, Fortran, any of the Fortran compilers, or the GCC compilers that exist, there are implicit rules in Make. The purpose of Make's existence is to take one or more input files to generate one or more output files. I'll take questions later. Yes. Yes. They are different things, but they do the same thing. The whole goal of Make is to make things. And so you have whether it's a rule or a recipe, you have a target with prerequisites, and the whole Makefile is a hierarchy of, at the top of the hierarchy, you have your main output file, usually like in C or C++, your output binary. And then there's a tree below that, which is all of your prerequisites. That's all your header files, all your source files, any libraries, all of that. So what a Makefile is we're telling, it's the build system where we're saying, this is all the prerequisites. This is how to build them. Now go and do it. So once you've in the rules, you've told Make this is what the prerequisites for every step in the tree are. It will keep and track that through the entire runtime when you invoke Make. Another really great feature of Make is that it will integrate with most compilers and do timestamp tracking. So if you touch a file and you have your Makefile configured correctly, it will rebuild that file. And we'll see that later on in the presentation. So the first thing, we're going to do a little bit of syntax. So there's a bunch of different ways that we can assign variables in Make. And you'll see that this looks pretty similar to Bash, and a lot of the syntax is designed to follow Bash. So the most simple is going to be the verbatim assignment. Now, even though in this assignment here we have no variables or functions that we're calling, you could put them in that assignment. It just wouldn't evaluate. Like if I had made the second line and the first line identical except for this colon, it would be a verbatim wildcard *.c, but it wouldn't evaluate it. It wouldn't actually call that function. And then if we say like sources2 is colon equal, use a simple expansion, then it would expand and call that function. They call it simple expansion, but really what it is it's unlimited recursion. So if you had like several functions stacked up here that all did the same thing, it would recurse down all of the functions until it's just text. There's no dollar signs or It's not turning on.
Yeah, no, it's on.
Oh, it wasn't before. So the three middle lines here that are all sources, they're all identical in terms of what they do. So in each case, they'll all find in the current directory, and the current working directory in Make is the directory that you've run it from, or if you invoke Make with the C flag, that tells you your current working directory. Anyway, so these three functions, that will find all of the C files in the current directory, whether we run simple expansion and use the built-in wildcard function, use the shell output. So what this will do is it will run the shell command, find, with those arguments, and place the output into sources. Now, there's another built-in function, which I find to be far more explicit than the shell output assignment, is literally just to use the built-in shell function. And that, this to me looks far more explicit. There's also the append operator, which is sort of assignment. Basically what that will do is that'll add the everything verbatim after the equal sign to whatever this variable is. So it will add the space and the W extra. This assignment operator is pretty cool. It's called the conditional assignment operator, and what it will do is the conditional assignment operator will say if C flags doesn't exist, if it hasn't been defined and set a value, then it will assign C flags whatever you've told it to. So say we have a variable called CC flags defined somewhere, and if our operating system hasn't defined C flags, then we'll use our own. So you don't have to do if def or if not equal, anything like that. You literally just use that one assignment operator. But there's a trap here in that this last line, if we look, it's a normal simple expansion, so it will set foo to whatever the expansion of bar is with the spaces and that comment. So if you have a comment on the same line in Make, this is a really big gotcha, that will be included in the actual text expansion of that variable. So that's kind of something you want to watch out for. Now we have a sort of listing of some of the built-in functions. There's a lot that aren't listed here, like the file name functions and some of the text functions, but it gives you some idea of what you can do with Make. And these aren't extensions in Make, so whether it's BSD Make or GNU Make, you should have access to all of these functions. So some text manipulation, so if we want to say, if we want to automatically list our objects as whatever our source is defined, we can just change the extension. If we want to then take those objects and add a build directory onto it, then we can use the add prefix function, which is one of the file name functions. And of the categories, the most are the file name functions, so stripping paths, stripping file extensions, doing all that's built into Make. And then we have our conditional functions, which are, like your logic. And even though these exist in Make, I've almost never used them. You really don't want to be including a lot of logic into your build system. You can generally do that just by selecting which target you're going to make. So or whatever it defines. You want to build that logic into your actual software, not the build system. So if you want to disable a feature for your software, you do that with a define that you pass to Make that gets filtered down to your application, that while it's building, it actually gets disabled at the source level. And then there's a for each function, which allows you to iterate over like a list of source files. if for whatever reason you needed to do something across all of your files. The value function will allow you to print a variable without expanding it. So if you have a variable that was declared verbatim with a $sign operator, so that's either a reference to another variable or a function, and you want to print that out onto, like echo it out to the screen, you can use the value function and then it will print that verbatim without expanding it. Otherwise, if you just did echo variable, it would do expansion on all of the references included in that. And then we've seen the shell function. It literally just spawns a shell, runs the command, and returns the output. And then the last three built-in functions are pretty important. So if you for whatever reason come to a condition in your build system where you need to stop building, there's an error function. And this is literally you call error and then pass it a string, and then make will say error and whatever you tell it to print. And warning and info, they're pretty self-explanatory. Error will halt the build at that point, but warning and info are basically the same thing, with the difference that one says info and one says warning. So it's kind of like a severity thing. And I believe that there's a command line flag for make to tell it not to emit info or warning, but it will always stop on an error call. So the next step up, we're kind of working from the bottom up in the hierarchy. If you were to follow all the trees to the bottom, then we would find rules. And so a rule is a shell command that make will use to produce your target. So you say if you look at these examples over here, these are all those implicit rules that are built into Make. And so you can see it's C, C++, Fortran, and Perl. I believe that's Perl. They all look pretty much identical. There's a lot of automatic variables in there that you guys don't know what they mean, but basically we're calling the C compiler with the C flags, telling it to give us an object file. The $@ is an automatic variable that says whatever my target name is, so this %.o is our target, this %.c is the prerequisite. So we're building an object file from a C source file. So that would give us the object name here and the source name here. This $caret is the first prerequisite. So these rules all use pattern matching. They all look at the file extension. So and you can define a rule for any file extension you want. You don't have to use C or O. Make really will work with anything. You just have to tell it what to do and how to do it. So the implicit rules that are here, they get obsolete quickly, because if you'll see later, like we're going to do automatic dependency detection, where it will only rebuild a file when that file is changed. You can't use the implicit rules, because then you have to pass more into the compiler, more information. But basically what this is when you're building, let's take C for example, when you're building an output binary and you have multiple source files, each source file needs to be compiled into an object file. And that's the same for a library. So if you have a library with 27 source files, each one of those source file needs to become an object file, and that's exactly what this is doing. This would give you all of your object files. So the next step up is we have recipes. So here we define sources as main.c, but we could easily use a wildcard to collect all of the C files in the directory. And then objects, it will essentially does like not a regex, but like a find and replace. It replaces .c with .o. But with recipes, it allows you to define a set of global targets. So if you have ever run like make clean or like make all, each one of these targets, so like all here and foo here, those are our global scope targets. But even if we look at rules like this %.o, if this was main.o, that's the target for that rule. So in this syntax here, this is how we tell Make what the prerequisites in the hierarchy are. So if and this isn't necessarily how I would do a Makefile in the wild. It just shows you a better idea of how that hierarchy can work. So if all is our default target, so the way that Make works is the first defined target is the one that gets run by default with no, like if you don't say make target, if you just run make, it will run the first defined target. So what a lot of people like to do is make all the first target and set it and forget it essentially. So the target is on the left here, then you have a colon and the prerequisite list for that target. So all is what's called a phony target, and a phony target is a target in Make that produces no output. In Make, if you don't have an output file that's considered up to date, Make will run every single time. Even though we want it to run every single time, it's a good idea to tell Make that it's in fact a phony target. So in this case, all, because it doesn't create a file called all, and clean, like similarly, doesn't create a file called clean. We declare them both as phony, just so that way Make knows that it doesn't have to worry about creating a file. So if we look at target, the target expands to foo. The target foo, the recipe, requires objects, but objects, as you recall, expands to all of our object files. What that's going to do is it's going to say, Make is intelligent. It knows that for every object here there exists, so in this instance objects would expand out to main.o. It knows that in the current directory that you're looking at there exists a main.c, so you must be building main.o from main.c, so it will use the implicit target for C. And what it will do is it builds all of the prerequisites. So in order for all to be considered complete, it will build target. It will follow that tree down. Well, this should say target, but it accomplishes the same thing. In order to build foo, it goes down the prerequisite chain to objects and will build each object as needed until foo can be run. Once all of the objects are built, then it will run the shell script that we have down here, which actually will link our final output foo. And that's just the compiler without the -c option, and that tells GCC to emit a runnable binary. And again, the $@ is the target, so it would just be GCC-o foo, and the $caret is all of our prerequisites. So if we had several objects that we were linking together, this would expand to all of them. So main.o, the foo.o, bar.o, it would include all of those. Later on in the talk, I actually go through all of these variables, and it can be used as a reference. Yeah, right here. Yeah, whitespace is often important because with Make, everything is verbatim. Like back in this, when I said that this comment here, these spaces and that comment would be included in the expansion of this variable. Whitespace is important. So in this syntax with these rules here and the recipes, you always have to have whitespace. So you have the target, the prerequisite, and then you have to have whitespace, which is, it could be 1 space, 2 space, 4 space, but I like to use tabs. It's to each their own kind of deal. But wherever you look, this sort of syntax is important. But even if you have a recipe that has no bash underneath it, it still has to have that white space between there. I'm fairly certain that if you deleted this new line here, it would error because there's I can't remember the syntax of the error, but you would probably get an error message. So if we look at this example makefile, we can see that there's a number of automatic variables in use, and there's also a good example of an order-only prerequisite, which is something that isn't very commonly understood about Make. So let's go through it again. We define our source files, we have our objects, but this case we're going to place all of our objects in a file called build, and you'll see later that that's where our order-only prerequisite comes into play. In this case, you'll see that our only phony is clean because we don't bother using an all. The target, the first rule that will be built, so if we run make, it will run this target, which it will expand out to foo, and its prerequisites are the object files. But now we have this order-only prerequisite. If you put a pipe in the list, the prerequisite list, everything following that list will be an order-only prerequisite. And to be honest, the name order-only isn't very descriptive because it doesn't mean anything to what it will actually do. So the way that make works is that if any of the prerequisites are updated, everything in the prerequisite chain above that gets updated. So if one of your header files gets modified, you want it to rebuild the source file, any source file that includes that header, and any binary or library that includes that source file. You want the whole chain to get updated. But for instance, if you have a build directory, anytime a file is modified in a directory, that directory gets touched. So you don't want to rebuild every single time that directory gets updated. What an order-only prerequisite does is it prevents prerequisites higher in the chain from being rebuilt. Does that make sense? So if for some reason your directory gets touched, it won't necessarily rebuild everything unless something that's being tracked gets updated. So anyways, we get back to current target. So this will expand out to the object file. So -o, if you've ever used GCC, is the name of the output file. So it makes sense that that output file is being immediately followed by the target of our rule, because the target of the rule is the object file, the name of the object file. And then if you remember your GCC syntax, you have to include the name of the source file that you're building. In this case, that would be the prerequisite. And if we notice here, the $ and the caret is it will expand out to the first prerequisite. In this Makefile, we're actually not defining CC, and sometimes it's not defined at the OS level. I find a lot of times it's really good to be explicit about what compiler you're using, because then that way you can switch between GCC and Clang at any point in time. You can also switch to like a GCC cross compiler if you're building a library. And then so another cool make variable that I rarely use is the $? And that will expand out to only prerequisites that have changed. So if for instance you're building a library, you don't need to repackage the whole library every single time. Like if you change one header that updates one source file, you only want to rebuild that one source file and then repack that one source file into that library. Now, packing a library is not necessarily a time heavy, so this is one of the reasons why I've never done it, but it's actually fairly cool. If the recipe that is building your library only looks at prerequisites which have changed, it would save a lot of time, especially if you're building a large piece of software. So a really, really cool part about Makefiles is automatic dependency. And it's a little bit complicated, it looks like, but the thing is that once you have these lines in your Makefile, they don't need to change ever. So once you understand what it's doing, you can integrate that into any build system you want. So let's take a look. GCC and Clang have a set of arguments, this MT, MMD, MP, that all instruct them, the compiler, to build this dependency file and put some information into that file. And if you were to open one of these dependency files, it would look quite a lot like a Makefile in that it has the target and the prerequisites in that chain. And what it does is, when you tell Make that those files exist, this include line at the bottom of the file, it says these files exist, include them, inspect them, and use that in the build process to look at the timestamp when it was created and compare that to the dependency file. If the source file is newer than the dependency file, then build everything above it in the chain. Does that make sense? So it's actually it's actually it's pretty important that the last lines end at the end of the file. Really, it's only the dep files recipe and the include that must be at the bottom of the file. I figured out why that needs to. Well, I figured out why it needs to be at some point, but I've since forgotten. It has something to do with the internal mechanics of Make and the way that it actually inspects the dependency files. But basically, just know that you have to have all of that at the bottom of your file. So what you would have is you would have all the defines at the top. You would have the rule defined, and this looks quite similar to the implicit rule. So if we go back here, you can see this implicit rule. There's some things missing out of here and out of there. So we can see that if the object file is our target and the C file is a prerequisite, that also makes this dependency file a prerequisite, because depdir is the directory that we're putting all of these dependency files. And then we also have an OrderOnly dependency prerequisite called depdir, which is again just going to make our depdir directory, and that's it. We you know, the line to trigger your compiler to build the file is identical except for the addition of the step flags. So the only thing that we're doing different is making the dependency files a prerequisite for building that file, the directory where we're going to put those dependency files, and that's optional. You don't even need to do that. So it's fairly simple, but it kind of all looks like magic, and in a way that's kind of Make's style, is to look like magic. So right here I've built a template Makefile, and if you follow the URL at the bottom right, it's shortened. It just goes to a GitHub gist that I've created. The only thing that you should have to change in this file is the name of your target binary. You can leave it foo, but it will always create a file named foo. So if you were to create a C hello world, put it in its own file, and then drop this Makefile in that file with it, it would build you a runnable binary. This contains all of the necessary lines for automatic dependency tracking. It even includes some special things I like to put in my Makefiles, and that so if you ever see in a Makefile an at symbol in front of a command, a shell command, then that instructs Make not to print that line out onto the screen unless you've told Make to make verbose. So when you build this, it will say cc main.c, and then it will say ld foo. That's all it will print unless you tell make to run verbose.
Where's that file at? I'm not in the Slack yet. It's at the bottom, right there.
It's typable. It's so. Does anybody have any questions?
Can you go back to the previous slide so I can type over? How is CMake different from me?
To be honest, I really haven't used CMake as of yet, but the plan is that I will learn it and I will teach a class on that too. Because to be perfectly honest, I've been wanting to get rid of Make from my life for a while because it's useful, but it's still pretty limited. And as smart and intelligent as Make is, it seems like CMake is 1,000 times more intelligent.
CMake is more difficult to use or easier to use than Make?
I think it's like the comparison of C and C++, Make being C and CMake being C++, where there's a lot of hand grenades in C, but there's a lot of leg mines in C++.
So what would you say are some of the strengths of Make?
A relatively simple Makefile, like the one that you see on the screen right now, could build literally hundreds of source files. The only limitation that this has currently is that if you have any subdirectories with source files, it won't see those because the source's wildcard expansion doesn't look in subdirectories, but it would be trivial to change that.
How much work do you have to do to modify a template to work between projects?
I would say, depending on how complicated your project is, you're looking at a one-line change to literally change the output binary. But there are things that this is missing, like if you have an include directory, which includes all of your headers, you would have to make a new variable that says this is the include path, and then make a C flags. The ways that I would upgrade this is by doing that, but also by defining what my compiler is explicitly, setting C flags. So I want to be explicit about what warning levels I'm using, what I'm passing to the compiler, what I'm passing to the linker. Like you'll see I use LD flags down here, but that's, well, now you can't see it, but you can see at the bottom of the screen down there we're using LD flags, but I've found that most operating systems don't define LD flags. And when you use a variable that's not defined in Make, it's effectively like including a variable that has nothing stored in it. It's no text. There's no spaces appended or anything like that. But yeah, using this template Makefile, you should be able to build just about any project that you want to work on. So yeah.
So one of the strengths of Make is that you can have relatively simple Makefiles, and it could build a project of hundreds of source files. Are there other strengths of Make?
I've kind of went into that in the first slide here, is that it really is, if it runs on Bash, it will run in Make. CMake is a little bit more integrated, I think, in that it's more oriented to work directly with the compiler. It's integrated with Clang a little bit on a level that's I think helpful when you're using Make to build software, but you could use Make to, like, integrate Docker or set up Kubernetes. I know people are screaming hearing that, but if
Don't do that.
if you have a Makefile to set up Docker images and tear them down, it's just like having a Bash script that has all the commands in it, except it's a target that you run. It's designed for automation, and so it's kind of combining two things that really weren't designed to be combined. but yeah, I think that's definitely Make's biggest strength is that it's simple, but it can do literally anything, whether it should do it or not. And then so you can see the quote on this slide here. I encourage you guys to look up. There's a paper that someone wrote, or a blog post. I can't remember. It's a recursive make is considered harmful. I said considered evil here, just for reasons. There's a program called AutoTools. It's a suite of programs. If you've ever run a configure and then make install, that's AutoTools. If you ever look at the make file that configure generates, it's like 4 megabytes of garbage. Where we wrote a file that's, 100 bytes, and it effectively does the same thing.
So I've run into numerous occasions where that run the configure and run the make, and the make dies horribly.
Yeah.
Options for skipping over the configure or looking at the configure and then making my own make file so I don't die in a fire.
Yeah, so the question was essentially, I've run configure and I've run make, and in one of the processes that the whole process dies in a fire. What's the likelihood that I'm going to be able to make my own make file? And that's kind of a difficult question because make is very flexible and you can do almost anything with it. The problem's going to come in with the various flags that they're passing around to the compiler, the complexity of their source tree, where they're pulling libraries from, because a lot of times AutoTools will actually download libraries. It will curl a dynamically linked library from somewhere, and if you don't see that happening, it's something you could miss.
So I guess what I'm asking is, can you teach a class on AutoTools?
That's probably not going to happen.
Yeah.
I may teach a class on trying to reverse an AutoTools generated makefile
Yeah.
so that it's human readable and can be changed into something that.
Is the make file that's generated by config going to be a binary, or is that an actual text?
No, it's just like the files that I have in these slides.
Okay.
It literally generates a makefile
It's just you.
that's a text file, and when you run make, it groks that file, goes in and does more or less what I've explained here.
Okay.
And I will point out that there are some facets of make that I haven't gone over, like user functions. These are all things that I haven't really ever run into in all of the years that I've been using make. And also some of the magic, as magic as this stuff looked, the magic that AutoTools will use to achieve what it's trying to do. And I think that a build system, much like the code that you're building, should be self-explanatory to a point. Like, if you came across this in the wild, you would say, oh yeah, we're loading up C files, we're building them. There's a lot of variables in here that I don't understand, like what's this $@ but you could look up makefile $@ and you would get right to the documentation that says here's what it is, here's what it does. So while I think a lot of this is magic, when you break it down into its pieces and you understand the hierarchy that you're building and what you're doing at every step, it's really easy to move forward and integrate that into what you're doing. Even like if you're building one source file, if all you've got to do is run make and you don't have to worry about GCC and all the flags, and you can permanently put the flags you want in one file, it's so extremely helpful. Like, the cognitive load of just building your code should be just make.
So you mentioned some of the strengths of Make. What would you say are some of the weaknesses of Make?
Like I was explaining, that it's kind of magical in that you can see that it's doing stuff, but if you don't understand those bits, it's just complete gibberish to you. And at least from what I've looked at, CMake seems to kind of be the same way. I mean, it's using a little bit more plain English in terms of the directives and the automatic variables that you're seeing here, but it all seems like, you would have to Google basically every line to figure out what a CMake is doing in much the same way you would a Makefile.
So it adds a layer of opacity and
Yeah.
an abstraction.
But I think the rewards of making your Makefile and making it work and having it work forever until you break it it outweighs the cognitive load of learning it in the first place.
If you're doing big projects, you have to have something to automate the process.
Absolutely. Even if you have 10 source files, that would mean running GCC 11 times, once for every source file and then once to build your binary. After one file, doing it manually becomes a hassle. So, and don't get me wrong, you could do all of the things that are on the screen right now with a bash script, because what it boils down to is what we're building is essentially a bash script. But you would have to do all of the boilerplate. Make is great because it's simple, but it has all of that boilerplate.
Can you go over how the Makefile decides which targets to run?
So you mean,
Like, if you have a clean option, does it decide it's going to run everything before the clean option and then run the clean option? Or
No,
does it
so-
just skip to clean when you type make clean?
yeah, so the way that works is you have your Makefile, and here we have a list of 3 global targets, three recipes, all foo and clean.
Right.
If
So
you
type make foo,
if you type make foo, it will run foo and all of its prerequisites, and that's it. If you type make with no targets, it will effectively turn into make all. Whatever the first target defined is, it will run that target.
okay, so it doesn't run make all because it's called all, it runs make all because that's the first target it sees.
Yes, that's correct.
Okay.
And a lot of times, the other reason people will use make all is because there are multiple steps in their build process. Like, if your project has unit tests, a lot of times what they'll do is they'll have a separate file to build all the unit tests, that's what recursive make is. You make into another directory from your Makefile. A lot of times, one of the steps in the build process is to build all your unit tests and then run them. So all will be like build, test, and test.
Okay.
That's a lot of times what people like to use all for.
So if you use all and you put 2 target names with a space, it'll just run each target in series? Or-
That's correct. So if here we did all target space clean, it would, in order of where they're put, it will build all of what's in target. So build all of foo, and then it will build foo's prerequisites. And then once it bubbles back up, it will then run clean and effectively destroy everything you've just done.
Right.
But yeah.
Is make inherently single-threaded, or?
No, so there is a jobs flag that you can pass to make, which is dash J, and that will do one operation per thread. So if you do dash J8 and you're on a quad core machine with hyperthreading, it will put one shell command per core, essentially. So if it's in the process where it's actually invoking GCC, it will say, like one rule per core, basically. But also, if you have some of these like RM or Makedir, or that's considered a job that Make will run on a core, and when that job is finished, it will run in order. And I believe the way that it works is, if foo here has 30 files in this objects as its prerequisites, it will run out of prerequisites before it bubbles back up to all. You know what I mean? So it's not perfect, but it's the easiest way for Make to make sure that it doesn't try to do a thing before a file exists. And yeah, passing the J operator for building big files or big projects saves quite a lot of time. If any,
Are they smart, or am I hard coding? You have 8 processors. If you don't have 8 processors, cry.
I believe that I don't really know. I don't know if it's that smart.
Try and see.
I think
Only as smart as you do.
I think it probably it probably does because it's going to run what's it called? It basically will query the operating system for how many cores, and either it will report a warning that says only n number of jobs are available and cap to that, or it will do that many jobs, but some cores will have multiple jobs.
That's why you always just do make J and proc.
I don't think that you can do that, but you could do like a tilde and
You used to do expansion.
and do cat proc CPU number or whatever. There's a way to do that.
Yeah. I've seen and proc in production before.
Yeah. It all depends on what's installed in your system, but if you do the cat, the CPU info and another thing that I wanted to mention is everything that are in these slides is done with GNU Make, not BSD Make. So if you are a Mac user or a BSD user, I can't guarantee that the Makefiles that I've given you will be 100% compatible, but I like to avoid incompatibilities. So I'm trying to think of something specifically, like these wildcard built-in functions may not be built into the BSD version. So in those instances, you would probably just have to switch to the shell function, or possibly to the shell assignment operator, the not equals. Those are the only inconsistencies I can think of off the top of my head. But yeah, if you were to take this template file, it would take you all 5 minutes to integrate it into your project, even if you had a fairly complicated source tree.
Is Make GCC specific, or would it work with Clang or something like that?
Work with anything.
Yeah, Make will work with anything. If you can run it in your shell, you can run it in Make.
Okay.
That's what the CC variable is for.
Yeah, so
You can change
I could hard code this to run GCC, but CC, if you actually open up your shell right now and you do echo $CC, it will probably print GCC because that's what your built-in compiler is. But if you're on a system where, say, you're using Muscle and a non-GCC compiler, it's intelligent enough. You're essentially building your Makefile to be cross-platform-ish. Because if I took that code base and moved it to a system that's not using GCC, well then you don't have GCC, you can't build the software. There's nothing in the code base, I know, that's coupled to GCC, so it should be buildable on any C compiler.
So you said that we can basically do whatever we want with Make, right? So could I like set it up so that, say, I make my own like MakeFlash, and I just type that and it flashes things for me? Like I want to flash my Arduino and stuff.
Yeah, so the question was, if we can do anything in Make, can we make a rule, a recipe that says make flash? And the answer is absolutely yes, you can. So if your tool to flash your board is a CLI tool, perfect. Then all you have to do is embed that command in your Makefile, define that target as a phony target because it doesn't create any files. And in many instances, that's I use my Makefile to flash if you're using like JProg or any of the AppMel tools or some of the STM32 OpenOCD, any of that stuff. It all works there's no integration, but as long you're running the command in your shell. So you can use your variables you define. When you set your target file name, you use your target file name. All of the arguments that you're passing to that you can set in a variable.
Can I do something like put an rmrf slash in there?
Yeah.
And
So
like have someone try and pull from GitHub and make my project.
So this actually happened to me not too long ago with the B-Sides Connecticut badges. So if you look here, the clean target I pretty much always have as RMRF object adapter target. That's basically all my cleans are always that. And I was reorganizing my source tree so that all of my objects will be built into one directory. And yeah, I RMRF my entire source tree without having Git enabled. And so I rewrote like 40,000 lines of code. But yeah,
So I probably should be looking at my make files
Yeah,
before I type the make command.
in much the same way you wouldn't sudo curl sudo bash, you don't want to sudo curl sudo make.
Okay.
Can I make a girlfriend?
If you tried
Yes.
hard enough.
Echoes and it would ASCII print.
Yeah.
UTF-8 girlfriend, please.
The
Now I'm
colors.
terrified. of
So
everything.
what is the difference?
That little bit of knowledge is terrifying.
I've heard other stories like that too. People
And-
commonly destroy their whole projects using the.
And let me tell you, if you're building a very large source tree and you pass J8 and you have 4 cores with hyperthreading, it will use every less drop of performance
It
it can
really well.
eke out of your computer. In fact, I have a button that will turn my CPU governor from power save to performance anytime that I'm installing anything from the Arch Linux AUR because it's got a build. So I have by default I have J4 pass to make with my AUR client.
So you mentioned the concept of a phony target that doesn't output actual files.
Yeah,
So,
that-
so you can have a target, but talk a little bit about how do
So-
you specifically specify that a target is phony? You just prefix it with a dot?
Yeah, so if dot phony is kind of like a make directive, and there's a few of these, but this is really the only one you'll ever use. And since make, whether it's a recipe or a rule, it expects that your target, when that target build is completed, that target will be a file on your hard drive in the current working directory or wherever you tell it to be. Make expects that it will exist. If it doesn't, every time you run make, it will try to rebuild that file. So
it's using the dot in front. You could have multiple phony targets.
that's correct. In this case, we do. We have both all and clean our target because neither all or clean.
That's the syntax.
Yeah, right.
Anything after that is
Yeah.
phony target. Yes.
So it's just like objects here. If objects in this case is only going to be main.o because we're just essentially doing a find and replace. But if sources if we look at here, we're loading all of the C files in the directory with the wildcard function, and then find replacing and putting it in an object directory. In this case, objects is almost certainly going to be more than one file name, all space separated. So down here at the bottom, if we look at target and all of the objects as our prerequisites, this is going to be foo followed by a list of files whose names are separated by a space. Everything after that colon is all of your prerequisites. Generally speaking, you're pretty much going to be looking at more than one prerequisite because if your project is complex enough to be using a Makefile, you're pretty much looking at least more than one prerequisite. Especially if you're using automatic dependency, because now it's going to be looking at all of the headers in that you're using, and when the compiler generates those dependency files, so if you had like a hello world and you include a header in there, see we do MMD, which is user header files only, but I believe it's -mm. It'll include all headers. So if you do like a hello world that includes stdio, it will generate as a prerequisite for that main.c stdio.h.
Cool.